Hey, what's going on? It's your old pal, Mr. Cook, and we're gonna finish up the Unit 5 probability group work. So I've got through the majority of these problems, now we're just on the home stretch of working through these individual word problems. Okay, so number 10, it says we have a school that has 600 juniors, 150 of them are athletes, 75 of them belong to a club, 25 do both. Find the probability that a randomly selected student is, and then a bunch of different questions that it's going to ask off of it. So let's set up the data so it's easy to read. This is a prime candidate for a Venn diagram because number one, we don't have any probability or percentages anywhere. We just have numbers, and it's only two options. They either are athletes or clubs, for all these junior students. So I wouldn't use a table because they don't have two different sets of data, just one, comparing these two values. So let's make that Venn diagram. So the box represents all of the information, so all 600 students. And we make two circles to represent the two different categories that we're breaking these students into. One of them is going to be for the athletes, so the people that are involved in athletics, and then another one involved in clubs. You always want to start by putting together like the intersections. The more intersections, the better. So like if you had a 3-circle system, you'd want the very dead center one first, and you kind of work with it from there. In this case, we've got 25 students that are both in a club and are in athletics. So that goes in the middle. That's our intersection, where the students are both, in club and also athletes. We go to the next part over, which is 75 people in total belong to the club. Now, that means 75 people are in the club, so if 25 of them are also in athletics, that means that 50 of them remain in just clubs. And then, similarly for the athletes, we have 150 of them, so that means if 25 of them are counted already in the clubs, that means that 125 of them are in only athletics. And if we add these together, the students that are in either athletics or in clubs, we've got 125, 25, and 50, which is 200. So if we subtract that from the 600 total students, that means we have 400 students that are in neither clubs nor athletics. So now let's answer some of these questions. Let's find the probability that if we selected a student at random, that they're both an athlete and also in a club. This word "and" pretty much implies that we're going to be doing an intersection between the two. So the intersection between athletics and clubs is 25. So there's 25 of those students out of the total of 600, and that reduces down to 1/24. So that's our probability, 1/24, that if we pick a student at random, they're in athletics and also clubs. All right. Next, in athletics or a club. So or implies that we have the union. So, you handle the union the following way. You can either find the individual probabilities, so the probability that they're an athlete, the probability that they're in clubs, and then you subtract away the overlap. Because, if you count all of the athletes and all of the club members, you count that 25 twice. So you want to subtract away the intersection as well. But, you can just count up the numbers if you want when you have a Venn diagram written out like this. So it's like these people are just athletes, these people are just in clubs, these people are both. So you just add all three numbers up. So 125, 25, and 50, that gives you 200. So 200 out of the 600 students, which reduces down to 1/3. So you have a 1 in 3 chance of picking a student at random in the group, and they're going to be involved in one of these things, athletics or clubs or both. What about not in either athletics or a club? Well, those are the 400 students that aren't in these circles, so it'd be pretty easy. It's just the 400 out of 600, which reduces down to 2/3. And then athlete, given that they are in a club. Now, when it says given, we're talking about a conditional probability, and we're only talking about the people that are in clubs. So those people in the clubs, there's 75 of them. And of those, how many are also athletes? Just these little guys right over here, 25 of them. So 25 over 75 reduces down to 1/3. And that's our probability for the last part of number 10. All right, moving on to number 11. We've got the data tables. These are always super easy to work through. You don't even have to read through this situation. I mean, you can, but what's the probability a student is enrolled in both Spanish and taking chemistry? So and implies intersection, so we just find where they line up. Spanish and chemistry, that's 35 students. And we take that out of the total amount of students, which is 136 of them. And there's your probability. I don't believe that reduces any further. No, it doesn't. So that's as good as it gets. What's the probability a student took French given that he or she took physics? Well, given that they took physics, that's conditional. So we're only dealing with the students that are in physics. So there's 33 of those. And of those, how many of them took French? 10. So 10 out of 33, that's your probability for that one. Last one, are preferences in science and foreign language independent? So we're just doing another proof of independence here. I guess since we did the conditional one before, let's do the product one, the product rule one. So the product rule one comes from the conditional probability. You know, the formula for that. Probability of A given B equals the probability of the intersection of the two events over the probability of the given event. Now, if these two events are independent, so we assume that they're independent, then that means that this conditional probability doesn't depend on B at all. It's just going to be equal to the probability of A. So that's what it becomes if they're independent events already. So the probability of A now is equal to the probability of the intersection of these two events over the probability of the conditional event. So now, if I just multiply over the probability of B, I get my formula. The probability of A times the probability of B, if these events are independent, should be equal to the probability of the intersection of the two events. Okay, so that's the product rule that we're going to use to show independence. So let's, first off, it's a science and foreign language, so to prove independence, we need to pick one of them. So I'll pick a science, let's go with physics, because I like physics. And then for a foreign language, let's go with French, because, you know, the first one on the list there. So let's, try and see if these two probabilities are equal to each other, the product and the intersection. So we first write it out, so we're looking for the probability that if we pick a student at random, they're in a physics class, and we multiply that times the probability that we pick a student at random, they're in a French class. And we see if that's equal to the intersection of the two events. So they're in both physics and also French. All right, so the probability that a student's in physics, that's 33 people that are in physics out of the total 136. And the probability that a student is in French, so the French students, there's a total of 34 of them. And that's out of the total 136 again. So we're going to see if that's equal to the probability of the intersection of the two events. So the probability of the intersection is the students that are in physics and also in French. So there's 10 of those out of the total number of students, 136. So let's just compare the decimal values and see if these two are the same. So do the first one, 33 over 136 times 34 over 136. And we end up with that decimal. Now let's see if it's the same as this one. 10 divided by 136. No, not even. Well, I mean, it's close, but it's not the same. 0.06 and 0.07, those are off. So these two are not the same. And what that implies is that this is not independent. And that means that they're, dependent. So that's all that you need to do for your proof. All right, moving on to the last one, number 12. So I'm going to need, let's see, do I need more space for this? No, this is going to be two iterations of a tree diagram. So I know this is going to be a tree diagram because it's broken up into underclassmen and upperclassmen. That's, one little category. And then of the upperclassmen and lowerclassmen, are they in engineering or not? So, it's just two separate branches and that's it. Or, two sections of branching for the tree diagram. So it's pretty easy. Let's do the underclassmen and upperclassmen first. So upperclassmen up, underclassmen un. And then if they're in engineering or not in engineering. And then same thing for the other one, engineering, not engineering. So there's our branches, 4 options at the end there. And then let's read through the information. So we have 62% of the students are underclassmen, so that's 0.62. And then 100 minus 62% would be 38%, so that's 0.38. So 38% of the population is upperclassmen. So of the 40% of the underclassmen are engineering majors. So underclassmen, that's 40%. And that means that 60% would be, that wouldn't be in engineering majors. And then 38% of the upperclassmen. So then 20% of those are in engineering, so 0.2. And that means that 0.8 is not in engineering. So once again, just like that previous example that we had when we had the tree diagram, you want to find the intersections of the events and kind of outline what each of these individual probabilities mean. Like each of these ones are like the probability that if you pick a student at random, it's an upperclassman. That'd be this 38 right here. Each of these are conditional probabilities. So like this one, for example, this 0.6 is the probability that a student is not an engineer given that they're an underclassman. That's like a 60% likelihood of happening. So each of these are conditional probabilities. Then we're going to find the intersections. So like, the first one that I could find is the probability that I have an upperclassman that's also an engineering major. That's the intersection. And, again, based off of the, did I have that formula up here? I thought I had it written. No, I guess not. Well, so to find these intersections, again, like I just use I do have it. I use this formula over here. The probability that I get the intersection is equal to the probability of one of the events times the conditional probability of the other event based off of the first event happening. So like, for these ones, to find the intersection, I just take this and multiply times that, and that gives me the overall probability. So like this intersection would be 0.38 times 0.2. Let's find what that is. 0.38 times 0.2. So 0.076. And then I do all the other ones also. So 0.38 times 0.8. That's 0.304. 0.62 times 0.4. 0.248. And then the last one, 0.62 times 0.6, 0.372. Okay, so that finds each of our individual probabilities. Now we're probably set to answer at least two of these three questions. What's the probability that a randomly selected student is an underclassman and an engineering major? So and means intersection, so that's why we found all these intersections over here, so we just got to trace it down. So underclassman and engineering majors, so that'd be this one, 0.248. What's the probability a student is not majoring in engineering, so NE, given that they're not upperclassmen, so given that it's an upperclassman. So to trace that one out, it's we just started upperclassmen, and the conditional probabilities are these ones. So what's the conditional probability that it's not an engineer? So that'd just be 0.8. So that's easy enough. They gave us that information, or we derived it from the information they gave us. The last one is kind of a tough one, admittedly. What's the probability that a randomly selected student is an upperclassman, given that they're an engineering major? Well, we don't know the probability of engineering major, do we? Yeah, well, we kind of do. We know the probability that, an upperclassman is an engineer also, right? That's that one right there. And that an underclassman is an engineer, that's that one. So if we add those two together, we actually know the probability of, the people being, one of the students being an engineer. So we just add those two together, 0.076 plus 0.248, that gives us, that'd be 0.324. So that's the probability that, you pick a student at random, they're an engineer. Now, this question is saying, what's the probability that you get an upperclassman given that it's an engineer, right? Well, we can use the formal definition of a conditional probability to write this out. This probability that we're seeking out is equal to the probability of the intersection of the two events, so upperclassman and engineer, over the probability that the student is an engineer. We just found that part of it. So, and we also know all the intersections too. So, this just becomes a simple ratio. So 0.324 in the bottom. And then the probability that we have a student that's an upperclassman and an engineer, is 0.076. Then we just, use our calculator and find out what the decimal answer is. And it might even be able to be reduced to, simplified as a fraction as well. Let's see, so 0.324, and then math fraction. Yeah, cool. So it's exactly equal to 19 over 81. Neat. So there's our last probability. Let's circle them just, to kind of get the answers out and everything. Okay, so that's number 12. If you still have some extra questions on like independence, mutually exclusive events, conditional probabilities, permutations, combinations, whatever, make sure to reach out to your teacher. So that's it for this. I'm probably going to do a couple problems from the extra practice, not a bunch of them, but just a couple of ones that I think are important. Okay, that's it for this one. Good luck on your test.